let's see how we can use the cross product if the two vectors are given in component notation. So same as with dot product, I will use the unit vector notation such that ax unit vector I plus ay unit vector j, and similarly b will be bxi plus byj. Same way as with the dot product, I will use a distributivity rule, which is axi plus ayj cross bxi plus byj. So I'm gonna be doing this cross this plus this cross this plus this cross this plus this cross this, same as before. Let's see how that goes. First term, axi cross bxi, same as with the dot product. I can extract all the scalars out, put them together, because scalars commute under multiplication. But as I take the cross product of what's left, which are the unit vector, I need to be very careful to maintain the order, because as we've seen before, you remember that A cross B is different from B cross A. So for the first term it doesn't matter, they're both I, but for the second term, as I'm doing axi cross byj, I need to be very careful to keep the I first and then cross it with j. Similarly, the third term will be ayj cross bxy. Therefore, again, for those two, doesn't matter whether you write aybx or bxay, since they're both scalars. But for the unit vector, this must be j cross I and not I cross j. And the last term, ayby j cross j. Now, the same way as we figured out the dot product, let's make a little picture. I is here, I is still here, and if you take the cross product between two vectors which are parallel to each other, you know that the answer is 0 vector. Similarly, as you're going to be dealing with j cross j, since those two vectors, which happen to be the same, are collinear, their cross product is 0. If you were going to do this in 3 dimensions, you would end up with k cross k, and this also is 0. Therefore, up, bang, 2 less. So really we have to only take care of the cross terms. Again, we can deal with this easily. Oops. I is perpendicular to j, which is also perpendicular to k, etc, etc. So therefore the cross product between I and j will always be magnitude of I times magnitude of j times the sine of 90. This is 1, this is 1, this is 1. Therefore really the magnitude of I cross j is 1, the magnitude of j cross I is 1, the magnitude of k cross I or j cross k, when you're going to be dealing in 3D, is always 1. So at least we know that the magnitude is 1. Now what is its direction? Remember, if you take in the cross product, it's going to give you a vector, so if you do I cross j, you're going counterclockwise, and therefore the vector you're going to obtain is a vector that is perpendicular to both I and j going towards you, which is the one we call k. Therefore I cross j is equal to k. Similarly, as we're going to be investigating j cross I, really now you're going j sweeping towards I, which is the same as going clockwise. In this case, you'll end up with a vector going inside the plane, which is opposite to the conventional k. Therefore, you'll end up with minus k. Another nice, easy way to remember is this: I, j, k, I, j, k. I cross j give you plus k. J cross k gives you plus I. K cross I give you plus j, etc, etc. So whenever you're going towards the right, you end up always with a positive. While if you try to cross towards the left, you end up with a negative. So the convention is right positive, left negative. Therefore, k cross j will give you minus I. J cross I will give you minus k. That was the one. I cross k will give you minus j. So it's a nice mnemonic trick. So this one will give me plus k, and this one will give me minus k. Therefore, a cross b will be ax bx k minus, whoa, this must be y, typo, sorry. And the other cross term is ay bx times k, or a cross b, I can factorize the k out, ax by minus ay bx k. So again, a cross product gives me a vector, and this will give me the magnitude of that vector. If ax by is bigger than ay bx, then it's going to give me a vector going out of the page towards me. If ax by is smaller than ay bx, it will give me a vector going into the page, which will refer to the case of going clockwise. Now this is messy, obviously, especially if you do 3D. Dude. So faster method, matrix. So really the cross product is very correlated with what we call the determinant. So please review this. It's standard algebra results. All you have to do is set up the unit vector ij, first row. Then you're going to put the component of the first vector, and remember the order is important, so this is going to be the first row, this is going to be the second row, or rather, if this is the first row, this will be the second one, this will be the third one. So this will be ax, this is a scalar, that's the magnitude of the x component of vector a, this is the magnitude of the y component of vector a, and then on the last one you're going to put your b vector, bx, by. That's what we call a matrix. Very, very, very useful. I'm sure you've seen it as you were learning techniques to solve system of equations. 2 equations to unknown, 3 equations to unknown, 25 equation, 25 unknown. That's the easiest way to go, because your computer and your calculator can do it easily. In case you don't have one, all you have to remember is the fish rule, which tells you that ax by, so as you start the fish you multiply those two together, and as you take a turn, up, put negative sign, and then you multiply those two guys again, ay bx. Look, same thing. This is what we call the determinant. If you use the matrix in 2D, you have to remember that if you take a cross product between two vectors in the plane x and y, therefore ij, you will end up with k. So don't forget to edit it by hand. If you don't like to edit by hand, just use the general case. In 3D, I, j, now you're doing 3D vector, therefore you can add a k, ax, ay. Now, if you're still doing 2D but you want to set up the matrix for 3D, no problem. If all your vectors are in the plane x and y, and he has no j component, no k component, no z component, so you put a 0 here. Similarly, bx, by, bz is 0, and use the same technique. The only little difference is the sign convention. The row 1, 1 is plus, 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 plus. The next one is negative, next one's positive, next one is negative, next one positive, next one negative, etc. Positive, negative. So you're gonna do in 3 steps. First, imagine vertical line here, vertical line here. The intersection will give you what you need, I. So all you have to do is evaluate this 2 by 2 matrix, which you already know how. All you have to do is use the fish. This times this minus this times this. In this case, you have 0 and 0, so this will give you 0. 0 times this I. Then you jump to the next term. Imagine that you're crossing the J. Intersection is this. Now you have to add the negative sign, and you do the fish method again with what's left. This is a 2 by 2 matrix, so ax times 0 minus 0 times bx, which also will give you 0. And it makes sense because you know there is neither any I or j component. If you vector into D, you will end up with only a k. And then you go to the last one, which will give you the k, and this will be ax by minus ay bx, which is exactly the same as this. So in this case, you end up with this matrix, ay times 0 minus 0 times by, 0. Then you can have the j component. Imagine this, so you have those two pairs as a new matrix. You're going to use the fish, ax times 0 minus 0 times by. So we end up with 0, which you will multiply by j, but remember, the second term is going to be negative by convention. So if it's not 0, make sure you don't forget the negative sign. And the last one, imagine this, so your 2 by 2 is this, ax by minus ay bx, and that's your k component. So that's the only one that survives a 3 by 3 matrix if you have 0 in the k component, but it should give you the same answer as this. If you end up doing a 3D problem, then no problem. You have AZ and BZ here and here. So the first term will give you AY BZ minus AZ BY. That will be your I component. The second term will be AX times BZ minus AZ times BX, and this will multiply minus J. And the last one, same thing, AX BY minus AY BX. So please use this as much as possible, especially when you're going to be doing 3-dimensional problem. And feel free to use the calculator to check your determinant value. Most calculators are able to handle determinant now. So this method is much faster than this ugly one. So feel free to use it.